understand the properties of limits. So we want to understand the properties of limits so we can apply them to evaluating limits algebraically. But before we can understand how to use the properties of limits, we probably should learn what those properties are. So we're first going to take a look at the properties of a constant function or of constant functions. And in these properties, we're going to let c be any constant, and we're going to let a be any real number. So our first property is going to be the limit as x approaches any a of the function c. So let's remember that limits talk about the height of the function. Well, this is where constant functions are very awesome when it comes to limits. And to help me demonstrate that, we're just going to look at a constant function. So let's just come in here and we can draw a constant function. Let's just call this function y equals 2. And here's the great thing about a constant function, is that for a constant function, the height of the function is constant. It's the same. So no matter what point I pick as an x value for this particular function, I know the height or the output will always be 2. So if I pick x equals -4, I'll get -4 comma 2. If I pick -1, I'm going to get -1 comma 2. If I pick +2, I'm going to get 2 comma 2. And let's just say I pick 5, I'll get 5 comma 2. So again, it doesn't matter what the x value is, because the output will always be 2, since this function is constant. Which means that for the limit, it doesn't matter what our a value is, because the height will always be c. So therefore, the limit of a constant is that constant. We can just drop the limit sign. Woo! Best property ever. Not really, there are some better ones in calculus, but this is one of the good ones. The next property is the limit of x. So the limit as x approaches a of the function x. And now this one isn't that bad either. And again, to demonstrate that, we're going to take a look at a graph. So if I were to graph y equals x, again, y equals x is going to bisect the third and the first quadrant. And here's the great thing about y equals x, is that if I pick an input of 1, the input of 1 is going to be, the input of 1 is going to match the output of 1. It's going to be 1, 1. And 4, 4. So for y equals x, the input is always going to match the output. So in this particular situation, we can just take whatever our a value is, and because the input matches the output, we can just do what's known as direct substitution, and we can just substitute the a in for the x. So that means the limit as x approaches a of x is just a. Nice and easy. Woo! Alright, so now let's just take a look at some quick examples of how to apply these properties. Since they're the only two that we know, these two examples are going to be pretty straightforward. So looking at letter A, we're looking at the limit as x approaches 3 of 7. So here we have a constant function of 7, which means the output or the height of this function will always be 7, meaning the limit will then also always be 7. Woo! Done. And let's take a look at one more. So letter B, we have the limit as x approaches 8 of x. And then as we look at the property, since we have the limit of a linear function with no coefficient, it's just the limit of x, we know that we can take the a value and we can use direct substitution to substitute that in and simplify this limit. So therefore, the limit as x approaches 8 of x is going to be 8. Alright, the next properties of limits we're going to be talking about are coefficients of functions. So let's say, for example, we have a limit as x approaches a of some constant times our function. Well, if we have the limit of some constant times our function, what we can do is we can factor out that constant from the limit. So we can come in here and we can take this c, and since it is a constant and it's multiplied by f of x, we can just factor it out like we would factoring a coefficient or a common factor out of an expression. So therefore, the limit as x approaches a of c times f of x can be rewritten as c times the limit as x approaches e of f of x. Now let's take an example, or let's look at an example of how that works. All right, so we're going to be looking at the limit as x approaches 3 of 2x. So if we look at this 2x here, 2x is really c times f of x, where c will be 2 and f of x will be x. So I can quickly just, rewrite this limit. I'm not going to have to do this every time I evaluate limits, but just to show the difference between the coefficient and the function here, I'm going to rewrite I'm going to rewrite 2x as being 2 times x, just to help demonstrate that 2 is the coefficient. And since 2 is the coefficient, that means we can factor it out of the limit. So we're going to end up with 2 times the natural log, woo! Brain fart right there. Let's try this again. We're going to get 2 times the limit as x approaches 3 of x. Well, we just learned a property at the limit of x, we can use direct substitution. So I can take the a value, I can plug it in, and that's going to give us 2 times 3, which gives us a limit of 6. So again, if our function has a coefficient, we can factor it out of the limit. All right, the next properties we're going to be talking about are the addition and subtraction of functions. So first off, we have addition. So we have the limit as x approaches a of f of x plus g of x. Now, properties of limits are great here because what we can do is, since it's addition, we can just pull them apart and take the limit of each function separately. And the same thing is true with subtraction. If we have the limit as x approaches a of f of x minus g of x, we can just pull it apart and take the limit of each individual piece. Now, while it works here, please do not assume this for all properties moving forward. We can't always just pull something apart and apply it to the individual pieces. For example, if you remember from pre-calculus, sine of a plus b did not equal sine of a plus sine of b. Remember, it did equal sine of a times cosine of b plus sine of b times cosine of a. So again, a lot of students fall into the trap of thinking, oh, I can always just pull something apart if it's addition. While it works great for limits, again, please don't make that assumption. But anyways, like I said, it works for limits, so let's move on and look at an example. So we're going to have the limit as x approaches 6 of 3x minus 5. All right, so based on what we just learned, we can pull apart the subtraction. So I'm going to be able to rewrite this as the limit as x approaches 6 of 3x minus the limit as x approaches 6 of 5. All right, so then moving on, we have the limit as x approaches 6 of 3x, and 3 appears to be a coefficient, which means we can factor this out, and that's going to give us 3 times the limit as x approaches 6 of x minus the limit as x approaches 6 of 5. All right, so if we look at the first term here, the limit as x approaches 6 of x, x is that special function where we can use direct substitution. So that's going to give us 3 times 6 minus the second term. We have the limit of a constant, and we know the limit of the constant is the constant, so the limit of 5 is just going to be 5. And we can continue simplifying to get 18 minus 5, or a final value of 13. next properties deal with multiplication and division of functions. Unfortunately, these are very much or very similar to addition and subtraction. What do I mean by that? Well, if we take the limit of f of x times g of x, we can separate it into its individual pieces and take the limit of each one of them. And the same thing goes for division. If we have the limit as x approaches a of f of x over g of x, that is going to be the limit of f of x all over the limit of g of x. So, again, just like addition and subtraction, we can break apart the pieces and take the limits of each piece individually. All right, one more note to make here is that for our second one, the properties for division, we can pull apart this limit into two pieces as long as the limit of g of x doesn't equal 0. Because again, remember, we don't want 0 in the denominator because that would give us an undefined function value. So as long as g of x, or excuse me, as long as the limit of g of x doesn't equal 0, we are good to pull this apart. All right, so let's look at some examples. So our first example here is the limit as x approaches -1 of 3x minus 1 over 4 minus 5x. So based on what we were just given, we can come in here and we can break this apart to be the limit of the numerator over the limit of the denominator. And then from there, we can break apart the subtraction in the numerator and the subtraction in the denominator. So this is going to give us the limit as x approaches -1 of 3x minus the limit as x approaches -1 of 1 all over the limit as x approaches -1 of 4 minus the limit as x approaches -1 of 5x. And yes, the fact that I have to keep writing all these limits over and over and over again is a huge pain. So, do you have to do it? Yes, absolutely, 100%. Because if you don't, it is wrong, because without the limit, we're describing the actual height as opposed to the behavior. So yes, you have to write and continue to write these limits. All right, so then continue working on here. We've got some coefficients that we can factor out. And that's going to leave us with 3 times the limit as x approaches -1 of x minus the limit as x approaches -1 of 1 all over the limit as x approaches -1 of 4 minus 5 times the limit as x approaches -1 of x. And then from here we can do the direct substitution with the x variables, and we know the limit of a constant is a constant, so this is going to leave us with 3 times -1 minus 1 all over 4 minus 5 times -1, which will be -3 minus 1 over 4 plus 5, giving us -4 over 9 as our final answer. So as you can see, these properties just keep compounding on each other, and we need to keep looking backwards in order to break down the limits as far as we possibly can until we can get this numerical value. All right, our second example is a little bit different because here we have the limit as x approaches -2 of x squared. But unfortunately, we haven't talked about how to take the limit that has exponents yet. So we need to remember ourselves, what does x squared really mean? Well, x squared is really the limit as x approaches -2 of x times x. Because remember, x squared is just the base times itself. Well, now that we have multiplication, now we can break it apart into its two pieces to have the limit as x approaches -2 of x times the limit as x approaches -2 of x. And because it is just the limit of a variable, we can perform direct substitution on both, which is going to give us -2 times -2, or an answer of +4. All right, and then our final property is properties of limits with powers and roots functions, or I guess power and root functions. I probably shouldn't have those s's in there. So if we have the limit as x approaches a of f of x raised to the nth power, what is kind of cool about the properties of powers and roots of functions is that if we have a function to the nth power, we can really rewrite this as taking the limit of that function and taking that entire expression to the nth power. So yes, if we have an exponent, it can be applied to the entire limit. It doesn't necessarily have to be just applied to that function. Now you might be asking yourself, wait a second. What you have written up there is just powers. What about roots? Well, let's remember a root really is a power. So for example, if we had the limit as x approaches a of the square root of f of x, this can be rewritten as the limit as x approaches a of the quantity f of x to the 1/2 power, which then can be rewritten as the entire limit as x approaches a of f of x to the 1/2 power. So yes, it works for roots as long as we can remember roots can be turned into powers. So with that being said, let's take a look at some examples. All right, so for our first example, we're going to look at the limit as x approaches 0 of x to the 4th. So using the property we just learned, we can rewrite this as quantity limit as x approaches 0 of x raised to the 4th power. So now we have the limit of just a variable, which allows us to use direct substitution. So this is going to be the limit as x approaches 0 of x, which turns into 0, and then 0 to the 4th power is 0. Voila! Done! Next example we're going to be looking at is the limit as x approaches 0 of the square root of x. And this is a similar situation to what I described above, so we can rewrite this as the square root of the limit as x approaches 0 of x. Well then, since we're taking the limit of a variable, we can just apply direct substitution. This ends up being the square root of 0, and we know the square root of 0 is 0. Done. Alright, so now that we know what the properties of limits are, let's look at some examples where we can apply them a little bit further. Alright, so in this example, we're going to let the limit as x approaches 2 of f of x equal 4, the limit of g of x, or excuse me, the limit as x approaches 2 of g of x equals 5, and the limit as x approaches 2 of h of x equals 8. And we want to evaluate the following limits, with the first one being the limit as x approaches 2 of f of x minus g of x over h. Alright, so let's talk about how not to solve this problem first. So, a lot of folks like to take shortcuts. And here's what they do. They just come in and they go, oh, okay, this is going to be the limit as x approaches 2 of 4 minus 5 over 8, which is 100% incorrect. Because you substituted, or you, the hypothetical, substituted in 4 for f of x. Nowhere in this problem does it say f of x equals 4. Nowhere. It says the limit of f of x equals 4, so the intended height is 4, not the actual height. Same thing for g of x equaling 5. Nowhere in the problem does it say that. It says the intended height is 5, not the actual. And then same thing for h of x. So please do not make that mistake. Another shortcut folks like to take, which will also be marked as incorrect, is they'll just come in and they'll do these steps in their heads. They'll just come in and say, oh, well, the limit of f of x is 4, minus the limit of g of x is 5, all over the limit of h of x is 8. And if you do this, while you will arrive at the correct answer, I won't see your thought process. So I'll assume that you meant that just f of x equals 4, g of x equals 5, and h of x equals 8, which they do not. So please do not try to take shortcuts here to avoid writing the limits. Yes, I know it's painful. Yes, I know it's awful, but you got to do it. So let's do this correctly. So we first want to take this and we'll break it apart based on the division. So the limit of the numerator, and we'll divide that by the limit of the denominator. Then we can pull this apart even more to get the limit as x approaches 2 of f of x minus the limit as x approaches 2 of g of x all over the limit as x approaches 2 of h of x. And now from here, since we have the limit of f of x, we can now replace that with 4. Since we have the limit of g of x, I'm not sure why that... Oh, because that's ink, not the highlighter. That would make sense. Sorry about that. Let's try this again. Now, since we have the limit of g of x, we can now substitute in 5. And since we have the limit of h of x, we can substitute in 8. So let's go ahead and do that. So we're going to be left with, let's see, 4 minus 5 over 8, which will be negative 1/8 as a solution. So yes, if you would have done those incorrect substitutions, you still would have ended up with the right answer, but we're at the stage of math where the work is just as important, if not more important, than arriving at the correct solution. Next up, we're going to take a look at the limit as x approaches 2 of 6 f of x g of x plus h of x. So we're going to do a similar thing here where we're going to want to pull everything apart first, and then we can substitute in the values. So I'm going to go ahead and pull apart the addition here. So the limit as x approaches 2 of 6 times f of x times g of x plus the limit as x approaches 2 of h of x. All right, from there, I can rewrite this as, let's see, I have 6 times f of x times g of x. So I can pull this apart to be the limit as x approaches 2 of 6 times the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x plus the limit as x approaches 2 of h of x. Another way you could do this problem is you might have noticed that 6 is a coefficient, so if you'd prefer to factor the 6 out of the limit and treat that as a coefficient, that is 100% a-okay as well. I'm just deciding here to use multiplication. So continuing on through, we have the limit as x approaches 2 of 6, and we know the limit of a constant is a constant, so that'll be 6. We're told up above that the limit as x approaches 2 of f of x is 4, so I can replace that with 4. And we're told the limit as x approaches 2 of g of x is 5, plus we know the limit as x approaches 2 of h of x is 8. And then from here, it's just simplifying. So 6 times 4 times 5 is 120, plus 8, giving us a final limit value of 128. All right, we're going to take a look at one more final example. We have the limit as x approaches 2 of f of x plus the square root of 5 times g of x cubed. So we'll just go ahead and start pulling this apart piece by piece. So let's see, we're going to get the limit as x approaches 2 of f of x plus the limit as x approaches 2 of the square root of 5 times g of x cubed. All right, I can pull this apart further looking with the square roots, so we're going to get the limit as x approaches 2 of f of x plus the square root of the limit as x approaches 2 of 5 times g of x cubed. Well, I can continue breaking apart the limit inside of the radical by factoring out the coefficient. So we're going to be left with the limit as x approaches 2 of f of x plus the square root of 5 times the limit as x approaches 2 of g of x cubed. And then finally, we just have to deal with that cubed part of the g of x. So we can continue coming in the limit as x approaches 2 of f of x plus the square root of 5 times the quantity limit as x approaches 2 of g of x cubed. And now that we have the f of x and the g of x isolated with the limits, we can go ahead and do the substitution. We know the limit of f of x is going to be 4. We know the limit of g of x is going to be 5. leaving us with 4 plus the square root of 5 times the quantity, 5 cubed, which is going to be 4 plus the square root of 625, which will be 4 plus 25, giving us a final solution of 29. And there you have it, folks. Properties of limits.